November 1944. The Franco-German border. A German combat engineer, a pioneer in the Army's terminology, kneels in frozen mud, trying to understand something that should be impossible. He has spent 3 days burying top mines, pot mines. The casing is compressed wood pulp, cardboard, and tar. The pressure plate is molded fiber. The fuse housing is ceramic. The seals are glass. The only metal anywhere in the device is the detonator cap, a component so small, buried so deep inside non-metallic housing, that the best Allied mine detectors in existence pass directly over it without registering a signal. He knows this because his unit designed it specifically to achieve that result, tested it, confirmed it. The Allied detectors are blind to these mines. That was the entire engineering objective, and by every metric his training had taught him to apply, the objective had been met completely. 300 meters away, American combat engineers of the 291st Engineer Combat Battalion enter the field. They are not using detectors. They are lying flat in the mud, rifles set aside, advancing on elbows and knees. One by one, they push thin steel probes into the frozen earth at shallow angles, 30 degrees, sometimes less, never straight down, sweeping forward a meter at a time, with the patience of men who have rehearsed this exact motion hundreds of times on training fields in England, and refined it against field manuals updated continuously from what had failed in Italy. In 4 hours, they clear a lane 40 meters wide. They find every mine. The pioneer writes a single word in his field journal afterward, a word military historians have since flagged with particular attention. Unverständnis. Not anger, not defeat, incomprehension. I have built the perfect invisible weapon, and the enemy is finding it anyway, and I cannot explain how. This is the story of why he could not explain it. The trail runs back through 3 years of escalating mine design, a Polish refugee's grief on a Scottish beach, and a baseball player's legs in the surf at Normandy. Before the answer can make sense, it is worth being clear about something the pioneer was not. He was not incompetent, and he had not made an engineering mistake. He had won every individual technical round of this contest. His design had defeated in sections every electronic instrument the wealthiest army on Earth had built specifically to find it. By any measure, his own training had equipped him to apply. The result kneeling in front of him in that frozen field should have been impossible. What he lacked was not skill. It was a conceptual framework that could account for what he was actually watching. The competition that produced this moment began in the sand of North Africa 2 years earlier, with 500,000 buried mines and a Polish engineer in Scotland who had just lost 12 friends. By 1942, Field Marshal Erwin Rommel had run out of nearly everything except improvisation. British submarines and aircraft were shredding his supply lines across the Mediterranean. Tanks arrived in dribbles. Fuel barely arrived at all. What he had, in quantity, was mines. And of his remaining resources, mines were proving the most reliable. At El Alamein, facing Montgomery's 8th Army, Rommel's engineers built what his own staff called the Teufelsgarten, the Devil's Garden. 2 parallel minefields, each roughly 5 miles deep, spanning the entire width of the battlefield. Roughly 500,000 mines in total, carefully layered. Teller mines, flat steel discs packed with 5.5 kilograms of TNT designed to destroy armored vehicles. S-mines, the notorious Bouncing Bettys, interspersed specifically to kill the engineers who came to clear the tellers. Anti-handling devices wired into the anti-tank mines, set to detonate if anyone attempted to lift one after planting. Scrap metal, broken tools, shell fragments, lengths of wire, scattered deliberately across the surface to generate false signals on every Allied mine detector, forcing every reading to be investigated and every investigation to consume time under open desert fire. Rommel stated his underlying calculation plainly. The mine was the poor man's army. It cost almost nothing. It held ground indefinitely. It forced the enemy to spend his most precious resource, time, removing it, and killed him in the process of removal. The British clearance technique of the period, walking a minefield, probing the ground ahead with a pointed stick or bayonet, was accurate but catastrophically slow, covering perhaps 100 square meters per man per hour on good ground, far less in loose sand or darkness. At that rate, breaching the Devil's Garden would take weeks the tactical situation could not afford. The British needed something that turned the minefield into a problem of physics rather than a problem of human endurance. They needed Joseph Kosacki. In the summer of 1941, Kosacki was 32, an electrical engineering graduate of the Warsaw University of Technology, class of 1933, who had run the repeater department of Poland's National Telecommunications Institute before the war. Commissioned as a signals officer, captured by the Germans in September 1939, interned in a Hungarian camp, he escaped in December 1939 and eventually reached St. Andrews, Scotland, where he taught Morse code to fellow Polish soldiers while quietly going stir-crazy with underemployment. Poland's exiled military establishment in Britain was, by most accounts, generous with rank and short on meaningful technical work for an engineer of Kosacki's specific background. Signals training for infantry replacements did not require an electrical engineer's skill set, and Kosacki had spent the better part of 2 years aware of the gap between what he could contribute and what he was actually being asked to do. On June 1, 1941, a patrol from the 10th Armored Cavalry Brigade, men Kosacki knew personally, walked onto a minefield on a Scottish beach near Arbroath. The British had laid the mines themselves months earlier against the threat of German amphibious landings and had simply failed to inform the Polish unit. None of the patrol returned. 12 men, lost on a beach they believed was safe, in a country that was supposed to be entirely behind the lines. Kosacki had been developing a mine detection concept before the war, a 1937 commission from the Polish Ministry of Defense that the German invasion had interrupted before deployment. In the weeks after Arbroath, he returned to the concept with a motivation that had moved well past professional interest. He built a working prototype in 3 months, largely using parts scavenged from radio equipment and whatever electrical components a Polish signals unit in wartime Scotland could reasonably acquire without raising questions about what they were for. 2 search coils mounted at the end of a bamboo pole, one connected to an oscillator generating a current at an audible frequency. When the search disc passed near buried metal, the electromagnetic balance shifted and the operator's headphones produced a tone. The power supply and amplifier rode in a wooden backpack. Total weight, roughly 14 kilograms. Manufacturing cost, trivial. The British Ministry of Supply had announced a competition for exactly this kind of device, reportedly prompted directly by the Arbroath disaster. 7 teams submitted designs, several from established British engineering firms with far greater institutional resources than a single Polish signals officer working from a barracks workshop. In the final evaluation, each detector was tasked with locating penny coins scattered across an open lawn. Kosacki's device found every coin, faster than any competitor's. The design was accepted. He received a personal letter of thanks from King George VI. He received no patent. He gave the design to Britain as an unconditional gift, with no compensation and no conditions attached. Because if his name appeared on official documents, the Germans occupying Poland might use his family there as leverage against him. For the rest of the war, the invention was credited to a series of pseudonyms, and the men who carried it into combat across 3 continents had, in most cases, no idea who had actually built it. He died in Warsaw in April 1990. A Polish military institute was named for him in 2005. For nearly 50 years between his invention and that recognition, most of the world had no idea whose design it was using. If accounts like this one, the forgotten engineers and quiet institutional decisions that actually decided battles, are worth your time, subscribing and leaving a like helps this kind of detail reach more people. 500 Kosacki detectors reached North Africa in the autumn of 1942. At El Alamein in October and November, British engineers used them to clear Rommel's Devil's Garden at roughly 200 square meters per hour, double the rate the bayonet probing method had achieved. Scorpion flail tanks followed behind, chains thrashing the cleared ground to detonate anything the detectors had missed. The minefields were breached. The Eighth Army advanced. Rommel began his final retreat from North Africa. German intelligence analyzed what had changed and reached a conclusion that was internally logical, technically correct, and strategically incomplete in a way that would take years to become apparent. The Allied mine-clearing advantage came from the metal detector. Remove the metal from the mine, and the detector loses the ability to find it. The flaw in this analysis was an assumption buried so deep that no one on the German side thought to examine it directly. That Allied capability was equivalent to Allied technology. That the detector was the thing finding the mines, rather than a tool operated within a larger institution that was simultaneously training its engineers to function when the tool failed. The Americans entering the same North African theater had observed something the German analysis never accounted for. Allied mine detectors failed constantly, against soil contaminated by shrapnel, against the deliberately scattered scrap metal Rommel's engineers used to generate false signals, against wet sand and mineral interference in the ground itself. When the detector failed, American engineers did not declare the ground clear. They went down onto their hands and knees and probed it by hand. The American mine warfare experience in North Africa had been expensive and specific, because the Army arrived in the theater with no systematic doctrine for it and had to build one in contact with the enemy. By the time the Tunisian campaign ended in May 1943, the Army had compiled after-action reports from every significant mine clearance operation it had conducted. Those reports documented, with granular specificity, what the detector caught and what it missed, which soil types masked its signal and which exposed it, the German practice of seeding scrap metal to generate false alarms, and the doctrinal countermeasure that followed directly from it. When the detector is unreliable, probe everything showing visual disturbance, regardless of what the instrument reports. The detector was a shortcut. The probe was the foundation. Remove the shortcut, and the engineer is forced back onto a technique that cannot be defeated by changing what the mine is made of. German engineering had not built this distinction into its calculations, and the omission would cost it 3 more years of design effort, millions of mines, and eventually a confrontation in a frozen field in Lorraine that would leave a pioneer writing the word Unverständnis in his journal. The Schützenmine 42 entered German service in 1942, and it was, in its way, the most cynically elegant piece of engineering in the entire German mine inventory. Not through sophistication, but through brutal simplicity, exposing a structural weakness in Allied detection doctrine that no amount of electronic refinement could fix. A wooden box, roughly 4 by 5 by 2.5 inches, with a hinged lid. Inside, a 200-gram block of cast TNT and a ZZ-42 detonator mechanism. Pressure on the lid deflected a retaining pin, which released a striker, which struck the detonator, directing the blast straight upward through whatever boot happened to be pressing down. The only metal in the entire device was inside the detonator itself, a small spring, a striker, a firing pin, a few grams total, buried deep within a wooden housing. Allied detectors, even sweeping their search coils directly over a buried unit at the slowest possible pace, frequently registered nothing at all. The electromagnetic signature fell below the detection threshold, further masked by the residual metal content that any soil exposed to shell fire inevitably absorbed. Allied soldiers called it the shoe mine, and the name captured its actual design intent precisely. It was not built to destroy vehicles. It was built to remove a foot. The logic behind that choice was explicitly logistical. A dead soldier is one casualty processed once. A wounded soldier, screaming, requiring a medic, requiring 2 or 3 other men to carry him to an aid station, imposes a substantially larger ongoing burden on the enemy's manpower and morale than a corpse does. The shoe mine was engineered to maximize that burden specifically, and it was mass-produced in the millions because its bill of materials was scrap lumber and salvaged hardware with no other military use. American combat engineers in Italy encountered organized shoe mine fields during the Cassino campaign in late 1943, sweeping ahead of their advance with SCR-625 detectors, an effective American instrument against metallic anti-tank mines, to a depth of roughly a foot, and the detectors reported clean ground. The mines detonated anyway. By the end of the Cassino campaign in May 1944, mines accounted for roughly 13% of American casualties in that sector. 13% from buried wooden boxes a detector could not find. Germany was not finished refining the concept. The glass mine 43 entered production in 1944 and pushed the minimum metal principle to its logical extreme. A glass bowl roughly 6 inches in diameter, a glass pressure plate, a thin glass cover disc. Later production versions used a glass ampule of sulfuric acid sealed inside a small aluminum can surrounded by flash powder. The weight of a foot crushed the can, shattered the ampule, and the resulting chemical reaction ignited the main charge, a detonation mechanism containing, in its most refined form, no metal whatsoever, nothing capable of generating an electromagnetic signature that any Allied detector's oscillator could register. Roughly 11 million glass mine 43 units were produced across 1944 and 1945. When Germany surrendered, an estimated 9.7 million remained in unrecovered stockpiles. The glass fragments these mines produced on detonation were invisible to standard medical X-ray equipment, making the resulting wounds substantially harder to treat than equivalent injuries from conventional metal case devices. Battlefield surgeons in Italy reported specific difficulty locating embedded glass fragments before infection set in, a complication that conventional shrapnel wounds did not typically present. Minefields of glass mine 43s are still being discovered in the Eifel National Park in Germany today, because buried glass neither corrodes nor degrades, nor announces its presence through any process soil chemistry can produce. The manufacturing logic behind the glass mine 43 reflected a specific German wartime resource constraint as much as any tactical insight. By 1944, German steel allocation was under severe strain across every branch of war production, and a mine design that consumed essentially no metal at all freed strategic material for tanks, artillery, and aircraft. The choice to build the perfect minimum metal mine was, from the German procurement perspective, as much an answer to a domestic supply problem as it was a tactical countermeasure against Allied detection. German engineers layered a final refinement onto the deception. Old scrap metal, deliberately buried near the wooden and glass mines, generating a continuous field of false detector signals. The strategy worked on 2 levels simultaneously. It forced every signal to be investigated, burning time and nerve. And it produced a specific psychological effect. An engineer whose detector screams constantly stops trusting the instrument. And an engineer who has stopped trusting his instrument moves slower, hesitates more, and is more prone to freezing at exactly the wrong moment. What the design did not account for was that the same scrap metal also told an experienced engineer something useful. Deliberate metal contamination in a field is itself a signal that real mines are probably buried beneath it as well. The deception was self-defeating against anyone trained to read the ground rather than simply listen to an instrument. And the probe, unlike the detector, was never asking whether a given object contained metal. It was asking whether a given patch of earth contained something solid that should not be there. That question cannot be defeated by changing what a mine is made of. It can only be defeated by removing the mine entirely, which is not a tactic any defending army can apply across an active front line. Mel Brooks understood this firsthand. In 1944, he was 18, a Brooklyn draftee who had tested into the Army Specialized Training Program before being transferred into the 1104th Engineer Combat Group, just in time for the Battle of the Bulge. Describing the probing technique decades later to an interviewer, he distilled the entire doctrine into 3 syllables, no field manual ever improved on. You would probe the earth lightly with your bayonet, and if you heard tink, 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 you knew there was something dangerous underneath, and you had to be careful. The phrase contains the complete engineering philosophy in miniature. Not a machine, not a frequency, not a sensor. A man, a piece of steel, and the discipline to listen to what the ground was concealing. Germany's deepest refinement was not the Glasmine 43. It was a problem the Glasmine's own success had created, and the solution Germany engineered for it remained a closely guarded secret until after the surrender. A mine invisible to every Allied detector is also, by the same physics, invisible to the soldiers who buried it. A German pioneer unit advancing back across its own minefield weeks later, at night, in rain, across terrain churned by artillery, exhausted men who could no longer remember precisely where each row had started, needed to locate their own mines with the same urgency the enemy did. A mine that kills advancing Americans is a tactical success. A mine that kills retreating Germans because their own engineers cannot relocate the safe lanes is a self-inflicted wound with no tactical value at all. Tarzan solved this. It was a mildly radioactive substance, its exact composition classified and maintained as a state secret for the entire war, applied as a coating to the surface of every top mine before burial. German mine detectors issued specifically to pioneer units for navigating their own fields incorporated a simple Geiger counter. When the search head passed over a Tarzan-coated mine, the counter registered a radiation signature invisible to any Allied sensor. German engineers could walk their own undetectable minefields with full confidence. The mines were simultaneously invisible to Allied technology and visible to German technology, by design. The secret held for the entire war. Allied intelligence did not crack it until post-war document analysis in the summer of 1945, and the reaction among the officers reading the decoded files was reportedly mixed. Genuine admiration for the engineering elegance, alongside the specific frustration of realizing how unnecessary the secrecy had ultimately been. The Americans had not been trying to detect the Topf mine electronically at all. They had been probing. In Lorraine, France, in late 1944, the 357th Infantry Regiment encountered a minefield that read as completely clean to every instrument available. The SCR-625 swept it and found nothing. The AN/PRS-1, the Army's experimental ultra-high-frequency detector, operating between 280 and 350 MHz, designed specifically to find materials that conventional electromagnetic detectors missed, swept it and found nothing. By every measurement available, the ground was safe to cross. The engineers went down onto their hands and knees anyway, because the updated doctrine specified exactly this response when detectors found nothing in ground that showed any visual or tactile sign of recent disturbance. They probed that single field and removed 12,000 mines. Bakelite, wood, compressed paper, glass, not one of them detectable by any instrument those men carried. Every one found by a technique that predates electronic mine detection by roughly 2,000 years. There was a visual dimension to this as well, one that German design philosophy had almost entirely failed to anticipate. An experienced combat engineer crawling through a field is not only probing, he is reading the surface the way a tracker reads a forest floor. The slightly different color of recently disturbed soil, the absence of vegetation over a patch that should be growing grass, boot patterns inconsistent with the surrounding terrain. The faint trace left by sappers who had worked the same ground 2 weeks earlier and left it subtly altered. Allied intelligence reports from Italy, France, and Germany accumulated highly specific operational detail on these signatures. The shoe mine in clay soil leaving a slightly raised rectangular outline after rainfall. The glass mine in sandy loam producing a faint circular depression after the first wet week. The top mine's compressed paper casing absorbing moisture at a different rate than the surrounding earth, creating a subtle color variation visible in low, raking morning light to a man lying flat at ground level. None of this knowledge existed in 1942. It was assembled mine by mine, field by field, casualty report by casualty report, over 3 years of combat and documentation and institutional transmission, and nothing in the German system for processing its own combat experience had an equivalent mechanism for generating it. June 6, 1944. Pre-dawn 40 miles off the Normandy coast. Jay Rencher, 23, from Idaho Falls, sits in a landing craft running through a sequence the Army had drilled into his unit, the 531st Amphibious Engineer Battalion, since December 13, 1943. Nearly 6 months of repeated practice landings on English beaches, run over and over until the procedure had stopped being memory and become reflex. Cut the obstacle cables, destroy the beach obstacles, build a road across the sand, clear the minefield. In that exact order, under direct fire, before the infantry waves arrived behind them. The rehearsal schedule itself was a product of the same institutional learning loop running everywhere else in the European theater. Earlier amphibious assault doctrine, tested against the much smaller scale of the North African and Sicilian landings, had been judged inadequate for an obstacle density and mine concentration that German engineers had spent 4 years preparing along a coastline measured in hundreds of miles rather than dozens. His commanders had told the battalion, without any attempt at softening it, what the projected casualty mathematics actually said. Within 2 hours of touching that beach, most of them would be dead. Not probably. The calculation had incorporated known mine density on the Normandy beaches, known German fire positions on the bluffs above, and the time required to complete the assigned engineering tasks under that fire, and it produced that specific number. Rommel had ordered between 5 and 6 million mines laid along the Atlantic Wall. He had wanted 50 million, a continuous belt dense enough that no landing force could survive the crossing at all. What he actually had was the largest engineered minefield in the history of warfare to that point, and by his own assessment, it was still insufficient. On the beach itself, teller mines were everywhere, lashed to wooden stakes driven into the surf zone, attached to iron hedgehog obstacles in the shallows, buried above the tide line in the dry sand. Each one a flat steel disc, roughly the size of a dinner plate, packed with 10 pounds of TNT, triggered by roughly 350 pounds of pressure. A running man could set one off. Any vehicle certainly would. Rencher's 3-man team included a soldier the unit knew primarily as Ham, a former professional baseball player whose entire physical future had been organized around the specific function of his legs. In the first minutes of the landing, in the water before the beach itself, Ham stepped on a mine. He was evacuated to a hospital ship. Both legs were amputated below the knee. When he regained consciousness and understood what had happened, he turned to face the wall and asked a single question, recorded by the men nearby. What does a baseball player do without any legs? He did not survive the day. One of the roads engineers later built across the Normandy beachhead was named for him. It still appears on the maps. By 7 that morning, 2 of the 3 men on Rencher's team were dead. Every assigned objective had nonetheless been completed. Rencher fought on through France, Belgium, Luxembourg, and into Germany, and was still in Idaho Falls in 2010, willing to describe the morning to a historian who came looking for him, still able to recite the precise order of objectives his unit had been assigned 66 years earlier without apparent hesitation. The specific kind of memory combat veterans often retain for the sequences that determined who around them lived and who did not. What made that clearance possible? 6 months of rehearsed landings, detailed advanced knowledge of specific German mine types and their typical placement patterns, doctrine refined continuously from every Italian clearance operation that preceded it, was the same institutional machinery that had been running since Kasserine Pass. The 1944 edition of Field Manual 5-31, Booby Traps, included detailed instruction on identifying shoe mine placement patterns from aerial photography, reading the surface disturbance signatures that different mine types left in different soil conditions, and recognizing the spacing intervals German engineers typically used when laying mixed metallic and non-metallic fields together. This was not general doctrine. It was specific, hard-won operational knowledge, extracted from men who had cleared those exact mines or died failing to, written into a form that engineers who had never personally encountered the mines could absorb before they needed it. By 1945, mines accounted for roughly 2.5% of American combat fatalities in the European theater, and somewhere between 20 and 22% of all American tank losses. 1 tank in 5 destroyed not by enemy armor, aircraft, or anti-tank guns, but by a buried device that frequently cost less to produce than a single day of a soldier's pay. Germany manufactured more than 3.6 million Teller mines between 1943 and 1944 alone, nearly 1.93 million S-mines, shoe mines in the millions, 11 million Glasmine 43s, and an unrecorded but substantial quantity of Topf mines and improvised wooden charges, assembled in the war's final months from whatever scrap remained in operating factories. The scale of German mine production was industrial. The American response, by necessity, had to be institutional rather than tactical. The British attempted a supplementary approach of their own. 4 Royal Engineer dog platoons, formed in April 1944 and deployed to France, trained to detect explosive compounds by scent rather than electromagnetic signature. The theory was sound. At an airfield near Caen in July and August 1944, the dogs struggled against ground saturated throughout with the residual scent of explosives from weeks of heavy fighting. In the Netherlands in February 1945, 1 dog platoon located 112 mines over 3 days of work. In the same operation, handlers and engineers working purely through trained visual inspection located 433, nearly 4 times as many, using eyes trained on exactly the surface signatures the accumulated Italian and French field reports had documented. A like on this video helps it reach the people who care about this kind of forensic military history, and a subscription means you won't miss the next one. Here is the forensic summary, stated with precision. The production numbers across the 3 mine generations tell their own version of this story. Germany's late-war mine output, measured by total units fielded, dwarfed its early war figures by a factor the Wehrmacht's own logistics planners had not originally budgeted for, each successive design requiring not just new tooling, but, in the glass mine's case, an entirely separate glass manufacturing supply chain diverted from civilian production. The escalation consumed German industrial capacity at an accelerating rate for a return that, against the American clearance method actually in use by 1944, approached 0. A steel probe pushed into the earth at a shallow angle asks not what a buried object is made of, but simply whether it is there. That question has no material science answer. It can only be answered by removing every mine from the ground, which is not an option available to a defending army holding a line. Germany had designed itself into a corner no further engineering could escape. Surviving correspondence between the Wehrmacht's Mine Design Office and the Heereswaffenamt, the Army Central Ordnance Authority, shows the design discussions through 1944 focused almost entirely on further reducing detectable metal content and improving radioactive coating concealment, with no surviving record of anyone in that chain raising the more basic question of whether American clearance methods still depended on metal detection at all. This was the irony the pioneer in his frozen field could not articulate but was experiencing directly. The perfect invisible weapon, found anyway by an enemy who had simply stopped looking with the instruments the weapon was designed to defeat. Meanwhile, the Americans were doing something the German mine program had no institutional mechanism to counter at all, learning at a speed German engineering innovation could not match. The after-action report from the Lorraine field went up the chain. The documented visual signatures from Italian clearance operations were redistributed to units that had never seen a glass mine. The AN/PRS-1's operational failure became a doctrine update that accelerated probe training, rather than waiting for a better detector. The dog platoon results from the Netherlands were assessed against the parallel probing results from the same operation, and doctrine reflected the comparison honestly. This machinery processed Kosacki's invention and Kosacki's invention's limitations. It processed the shoe mine, then the glass mine, then the Topf mine, each in turn, and emerged from each cycle with updated doctrine that closed the specific gap the latest German innovation had opened. Consider the span between February 1943 and November 1944 directly. At Kasserine Pass in February 1943, American engineers advanced into minefields with inadequate doctrine, dependent on detectors the terrain frequently defeated, without the systematic probing discipline or trained visual reading skill that 18 more months of Italian and French combat would build. By November 1944, the institutional descendants of those same engineers, trained on the accumulated documented failure of every clearance operation since Kasserine, cleared 12,000 technologically invisible mines from a single field in Lorraine in one continuous operation. In that same span, the German mine program had advanced through exactly 3 material innovations: shoe mine, glass mine, Topf mine. The American clearance system, over the identical period, had moved from fragile, single-instrument dependence to a fully integrated structure of electronic sweep, trained visual inspection, and systematic hand probing, with no single point of failure remaining anywhere in the sequence. Germany deepened one tool repeatedly. America built a system with redundant layers. When Germany defeated the tool of the moment, it had defeated exactly one layer. The system underneath remained intact and kept operating. Józef Kosacki died in Warsaw on April 26, 1990. Improved versions of his detector remained in active operational service with armies around the world through the First Gulf War in 1991. Nearly 5 decades of continuous use, spanning a Cold War's worth of conflicts in which the basic electromagnetic principle he had sketched in a Scottish barracks workshop never required fundamental redesign, only incremental refinement of frequency range and portability. He never received the patent, never sought commercial recognition, and never saw his name publicly attached within his own lifetime to a tool that carried his design in every functional component. Poland's post-war communist government declined to acknowledge him, in part because his wartime service had been to the Polish government in exile in London, a political affiliation the post-war regime in Warsaw had every institutional reason to erase from official memory rather than celebrate. He returned from wartime Britain to a country that treated him, for most of the remainder of his life, as though he had never built anything at all. J. Renscher came home, fought through to the German surrender, and was present in person at the liberation of Moosburg prisoner of war camp in the spring of 1945. He was still in Idaho Falls in 2010, married, still describing the order of the morning's objectives, still carrying what that single morning had cost. Ham's Road in Normandy remains on the map. The German pioneer who wrote Unverständnis in his journal, if he survived the war, if he ever read the post-war intelligence files describing what the Americans had actually been doing instead of searching for his radioactive coding, would have found his answer contained in a single principle, requiring no further engineering knowledge to grasp. He had been competing against an institution that converts failure into documented knowledge, distributes that knowledge faster than the next material innovation can be designed and fielded, and assumes from the outset that today's solution will become tomorrow's obsolete liability. That kind of institution cannot be defeated by defeating today's specific tool. It can only be defeated by defeating the institution itself, and the institution the United States Army built across 3 years of escalating mine warfare, from the sand of Tunisia to the frozen fields of Lorraine, was not a machine at all. It was a human habit, converting failure into knowledge, and knowledge into the hands and eyes of engineers lying flat in the mud at 30 degrees, listening for tink, tink, tink. There is a final detail worth setting down, because it closes the loop the pioneer's journal entry opened. The Tarnzen file that Allied intelligence finally cracked in the summer of 1945 included production records for the radioactive coating itself, a substance requiring its own dedicated processing facility, its own supply chain, its own trained handling personnel working under health and safety protocols that German industrial documentation from the period treated with notable seriousness, even by wartime standards. Germany had built an entire specialized industrial process, maintained in absolute secrecy for years, to solve a problem that the answer to made strategically irrelevant. Keeping a mine invisible to an enemy who had already stopped looking for it with the instrument the radioactive coating was designed to defeat. The engineering achievement was real. The strategic premise beneath it had been wrong since at least the autumn of 1943, and no one in the German chain of command overseeing the program appears to have revisited that premise even once before the war ended. If this forensic account gave you something to think about, hit the like button and subscribe. It helps stories like this one reach the people who care about getting the history right.